University. Brian, thank you for joining us today.
Thank you, everybody, and thank you, Renee. Okay, I guess we'll get started. So today's topic, thermal management of GaN FETs. Some of the subtopics we have are thermal resistance device comparisons to MOSFETs, and just comparison of different thermal paths. PCB only for heat spreading, where if you have a PCB and don't want a heat sink and just want to use the PCB, how does that work? Heat spreader and heat sink attachment overview. Thermal improvement with the heat spreader and heat sink. And last, let's see, where is it? There we go. A demo of a new thermal modeling tool. I'll give a live demo. You can see some of the calculations actually taking place behind the scenes, so you can see different mechanical configurations and see some of the cooling. Okay, let's get into some details here. And you'll see common statement here is that small chip scale devices such as GaN FETs cannot be adequately cooled. But we'd say yes, small chip scale devices can be adequately cooled. There are simple methods to do this. And why would that be? Well, if you look over here at the junction resistance from the thermal resistance from the junction to the board, you see it kind of lines up pretty well. The GaN FET dots in blue, the silicon MOSFETs in red, they're all in the same range. But then you look over here to the right in the green box, and you'll see that even though the GaN FETs are smaller, the thermal resistance from the junction to the case, the part where the heatsink would go, is actually lower, which is good, less resistance compared to the red line, which is silicon MOSFETs. So later on in the presentation, we'll see how to take advantage of that actual improvement. Now the first section, PCBs. For now, let's just look at the PCB without a heatsink. So here's a typical board. And one thing that's really nice is the copper that's already on the board conducts heat very well. So here's a typical board layout, I would say. You could see right here, for example, there's a half bridge, a top FET, a bottom FET. The gray outline would be where the GaN FETs would be. This top plane would be, say, V in, switch node in the middle, and the ground plane at the bottom. So just a plain board, no vias. You still see some good amount of copper there. We can draw heat away from the FET to different places. Now let's go one step further. What happens if you put vias off to the side of the FETs? That helps to take the heat that's already coming out of the FET into this top layer and conducting it down to other layers of the board. For example, down here, this would be a ground connection. There's likely to be a ground plane somewhere in the board, and that'll help conduct heat to that plane. Up top, the VN, and here the switch node. Even a partial plane somewhere else on the board, different layers will help conduct heat. Now to go one step further, you put vias actually under the bumps, the GaN FET. GaN FETs being chip scale, they're not always solder balls. A lot of the EPC GaN FETs have solder bars. This is one example here, and the black dots are not the bumps of the FET. These are in-pad vias, which is really nice because the junction of the FET is right directly over top. It's a very short mechanical path from the source of the heat down through these vias to somewhere else in the board. Okay, so that looks good. Now let's get some finite element analysis simulations. So these are the three same conditions. Here's the titles on the bottom: no vias, the side vias, and the vias under the bump. The top photos are looking down on the board. You can see the outline here in red. It's a little bit harder to see, which is actually good because it means the heat's dissipating throughout. And the second row of photos, that's a side view where the FET is on top of the board. This is the thickness of the board. And this line down here is basically the bottom of the board. So with no vias, you can see some heat spreading, but it's not as good as you'd like. The red represents the highest temperature. That's on the FETs. So yes, there's some spreading, but there's room for improvement. By the way, this is oftentimes good enough for many situations. If you don't have high power, and say if you have bursts of power coming out of the power supply, this might be sufficient. But since you have a board and you most likely have vias, why not put in some vias next to the FET? So with this one, you see the same basic condition of power going into the FET, but yet the FET is cooler just because heat is spreading out better throughout the board. It's going into different layers. It's not real obvious, but it is happening. You can see the green area moving, which is the next step above blue in terms of heat. And that results in a 22% decrease in the thermal resistance. And the third one here, this is the vias right under the pads. Here's the FET, the side view. There's an in-pad via coming down directly almost directly tied to the heat source of the junction of the FET, which is on this side of the FET coming down. And that's really even more effective. You can see the heat spreading down. And compared to the original condition over here, that's 33% improvement, a reduction in thermal resistance. So I guess the conclusion of this slide is that the under-bump vias, that's about the best. Let's look into that a little bit more. Via pad plated over. Once again, these are optional. This is not required for GaN FETs. In many boards, it works out very well. In some boards, because it costs more, some people would rather not do that. So it's an individual decision. But let's look into this some more, because it does do quite a bit. And in many cases, it can actually help avoid having a heat sink. So some of the details of constructing it. First, the wall thickness. This is the side view. This is the actual via coming down. The wall thickness be 0.78 millimeters. 0.2 millimeters per IEC standard. The hole diameter from one side to the other side, 7.8 mils or 0.2 millimeters. Annual ring, 0.35 millimeters. And plated over. Down here is kind of like a tilted view. So you see the copper plated over, and that's important to keep everything good for the actual pad with the FET. Non-conductive fill. The non-conductive fill, the conduction actually is dominated by the wall anyway. So there's not much benefit to having a conductive fill, and non-conductive fill has other benefits. So it's probably just as well, and that's what a lot of board houses prefer. So non-conductive fill works out well. You want the tented both sides of the board. Here's a solder mask tented over there. This can be used for under the bump and also close to component pads. If you have something that overlaps or very close, that's good. It keeps the solder from going down into the vias, which would be not so good. So this is usable up to 2 ounces of copper thickness, which quite often is the maximum thickness that is used in a lot of boards anyway. Now let's go back to the diagram here and look again. And this time let's look at the thermal models. Previously was the finite element analysis of the thermal flow. This time we have 2 FETs basically arranged in a half bridge, or they can be independent, but 2 FETs somewhat near to each other on a PCB. The little red line here is basically the junction, and the dot is the temperature of the junction of number 1, temperature of dot number 2. So the red text is temperatures at various places: ambient, case, the board in spot number 1, board in spot number 2. To the left, you'll see we call this a no heat sink thermal model. So the 2 sources, they look like current sources, but this would be a thermal source, one for each FET, and you can see the FETs are actually linked, and the ground is ambient. You see 2 grounds, just depending on how the circuit is arranged, but just like any other electrical circuit, you can have multiple grounds to make it more clear. So some conclusions in the general case here is the the thermal resistance from the junction, the red bar, to the board through the solder bars or solder balls, that's dominant. The PCB is used as the heat sink in this condition. So the heat goes directly from here down through the solder connection into the board and dissipates there. You can also ask, well, what happens here on the case? In this situation, the thermal resistance of the case to the ambient is larger. So it's really too large to have a meaningful impact on this one. Okay, you can ask, well, that works really well, but what if you want to get the absolute most heat out of the GaN FET that uses the heatsink, right? And yes, that's true. So we've come up with a good example of how to do this. You can have, here's a board. The green is a circuit board. The blue would be the GaN FETs, just like in the previous diagram, put somewhat close to each other, typically in pairs, could be half bridge, could be independent. And a heat sink on top. A few different things are these little screw holes here are actually used as spacers. Here's a side view. This part, the thin part goes into the board. The thicker part sticks out of the board, a 1 millimeter section. That creates a 1 millimeter gap. The GaN FETs are less than 1 millimeter, so there's space to put a thermal interface material on top of the FETs, and then take a heat sink and screw the heat sink down onto the screw holes. This has the advantage of maintaining a constant gap. It eliminates thermal stress from the top of the FETs, and it's just a good control system for constant pressure and repeatability. So it's relatively simple. It's easy to implement, and it's low cost. Use a standard heat sinks. Over here to the left, you can see the details on one particular spacer we found. Worth Electronics, the part number. I think it's available on DigiKey. I think I saw it there. Okay, let's look some more at this. The thermal approach. Here's a cross section of the previous diagram. Again, here's the heatsink on top, the two FETs mounted on the board. And you could also ask, well, what happens if you have other parts? You want a capacitors really close to the FETs. You don't want them to be outside the thermal situation. And no, that's true. Having them very close is possible, but not only possible, but it actually helps. It fills up the gap with something that conducts heat better than, say, a thermal filler or so forth. So having capacitors or other devices in there is actually good. All the components under the heatsink must be less than the height of the GaN FETs, obviously. You don't want to have them push it up. And the thermal pad must be mechanically compliant. In other words, when you put on the heatsink, it'll squeeze down a little bit. And all the thermal pads have specs as far as how they work. How much squeezing relates to how much thermal resistance. And one thing that also to keep in mind is the thermal pad must be electrically insulating to the operating voltage. That's because the GaN FETs, if you use a meter, like a handheld multimeter, you might measure open circuit between the case and the pins. But with just a little scratch, just a thin oxide, it's not meant to be electrically insulating, just a thin scratch could show a connection between the top of the case and the source pin. So the top should really be considered to be at the source pin, which in many cases is ground, but in the example of a half bridge, the source is the switch node, and that's the last thing you want, is to have the switch node connected to a heatsink and also connected to the ground of the bottom FET. So electrically insulating thermal interface material is really good there. And again, this shows the spacers. And a little note here is besides the capacitors, there's actually resistors work well to conduct heat. And there's also things that look like resistors that are actually aluminum heat spreading devices that are for sale. So those can actually be used also to enhance the heat flow from the PCB to the heatsink if that's needed. Okay, let's look at some of the properties, the considerations of the properties of the thermal interface material. So one thing that's good is to have a thermal conductivity that's greater than 3.5 watts per meter Kelvin. Now, this is different than thermal resistance. The higher the number, the better. This is conductivity, not resistance. So higher than this is actually better. So that's one good point. Next, it's how much compressibility. It determines the force on the die when compressed. So the GaN FETs can take quite a bit of pressure, but you want to have it designed so that it fits in your system. You wouldn't want to have too much pressure be put on, and certainly not enough. So data sheet of the thermal pad will help out quite a bit there. Next is the starting and available thickness. So as in the previous diagram, there was a spacer of 1 millimeter in that example. So you take 1 millimeter minus the installed height of the FET on the board, and that's what's left over for the thermal interface material. So you want to have that minimized, because the thicker the thermal interface material, the higher the thermal resistance. Now, if you want to have it too thin, you might run out of mechanical tolerance for manufacturability. So you select optimal compression. And once again, the voltage withstand capability. There's an example of a FET, which in an operational circuit will have a voltage applied to it, as compared to the heatsink, which may be grounded or may be considered grounded. Another point that I should have made in the previous slide is it shows a heatsink here, but instead of a heatsink, this could also be the chassis of a device. If you have a metal chassis and the metal chassis is bolted to something else or it works well to dissipate heat, instead of an aluminum heatsink, you can have aluminum plate, or you can have, say, a steel case. The concept is all the same, getting the heat from the FET through a thermal interface material to something else, and have a spacer to maintain a good space between, to maintain the good gap between the board and the top of the metal right here. One example of a very good thermal interface material is from a company called T Global. Here's their part number. And the conductivity is 17.8. That's very good. That really helps bond thermally the top of the FET to the heat sink or heat dissipation, heat plate, and so forth. So looking some more at the thermal gap filler, you can use this if needed. Sometimes it adds some good benefit, and other times it doesn't. We'll go through some examples later on in the presentation that shows that sometimes it just doesn't really add much, so you can save a little bit of cost. Other times it does add something. It works best for small devices. You can say, well, GaN FETs are small, but even within the range of GaN FETs, there are some tiny GaN FETs and there's some large GaN FETs. So the smaller device, the better it works. And that's because there's different paths. You have the top, which we discussed, going into the heatsink, the bottom going to the PCB. But this gap filler helps two other paths, from the PCB to the heatsink, and also from the sides of the FET, which is not insignificant. Here's a diagram showing the four sides that weren't previously discussed of the GaN FET. If you have gap filler next to them, that can help conduct heat away. And that can be a good percentage of the total area. Quite often it's combined with thermal pad. So thermal pad on top and the gap filler in light blue on the sides of the FETs. Gap filler selection, again, it should be a conductivity greater than 1, and voltage withstand capability for the same reason as the other one. You don't want to have electrical connection between the sides of the FET, which is source potential, and something on the board, or maybe come around here and contact the heat sink. One example of a good material is this particular part number from a company, Berquist. Okay, to go further, you have heat sinking and heat spreading. With heat spreading, you can have a plate such as this one, a copper plate, one you can define yourself and put the screw holes wherever is most appropriate for your design. And that effectively increases the thermal area, increases it in a way that uses copper, a big copper plate, which can be very good. And in some cases, that's good enough. You don't need a heat sink on top, but you also have the ability to add a heat sink top of the heat spreader. So you can have aluminum heat sink on top. That increases the surface area for heat flux exchange. The fins contact more air. So especially in airflow environments, that can really help. And again, heat spreading and heat sink can be combined, or they can be independent. And in this case, the heat flux still flows into the PCB. This is talking about heat sink, and there's where it goes. But even in the case, there's still heat that will flow into the PCB. So you will get some cooling from the PCB in addition to the heat sink or heat spreader. It's not either or. Now let's look at some heat spreader heat sinking performance, some more thermal simulations. So with this one, you can see with the heat spreader, you can see the two FETs down there in red. You can see the heat coming out. With the heat sink put on top of the heat spreader, you can see the FETs getting even cooler. From here, I think it says 41 degrees down to 34.9 degrees C in this particular example. And this is with 400 linear feet per minute airflow at 20 degrees ambient. Now let's look at the thermal model of what we just discussed. Now, yes, this is getting more complicated, but again, there'll be a demonstration in a few minutes. They'll show a calculator to take care of the complication of this model. But it's important to see it because it illustrates the point the previous slide just made, that there still is conduction into the board, even with a heat sink. So you have multiple heat paths, from the top of the FET up, from the bottom of the FET down, from the sides to different places, from the board into another component up, and so forth. So you can have quite a few paths here. In this example, TS, the temperature at the heatsink, is assumed to be uniform in the location of the FETs. It's midway between the center of the heatsink. Okay, now we'll switch to a live demo of a thermal simulation tool. And let's hope it comes up. Here we go. It's a tool that the EPC thermal engineers worked on. This is really nice. Right now it's written in Octave. Our plan is to get this onto our website as a calculator on the epc-co.com website so that anybody can use it. That work's continuing. We hope to do it, hope to have it completed this fall, hopefully end of October. And by the way, we're still taking suggestions and comments and so forth on this to make this more usable and more helpful for any situations you see that may not be covered. So for now, this is something that your local field application engineer, such as myself, can help you with. So let's start with a simple situation. Look at the diagram here, just one FET mounted on a board. Take an ambient temperature, say 20. Over here on the right, you'll see the temperature of the junction. Because it has 3 watts coming in, the temperature of the junction is, see if I can read that, 96 degrees. Okay, it's a bit warm because especially that's at ambient temperature of 20 degrees C, there's not much margin for increasing the ambient quite a bit. This is with a 4-layer, 2-ounce board. If you jump up to say an 8-layer, 2-ounce board, we'll go down from 96 degrees down to 90 degrees. So, okay, 6 degrees, that helps. Now, another part that's put in here is vias. At this moment, it's only in-pad vias. So let's click on this, in-pad vias. And you'll see them show up in the diagram right under the pads. And now we went from 90 degrees to 77 degrees, basically here. And you can see what nice help that is. But you can say, okay, that's good for one FET, but I have 2 FETs. I'm working on a half bridge. So, okay, there's a half bridge. Click here you can do. And there's 2 two FETs put close together. How close you can determine here, the default 2 millimeters, I'll just leave it there for now. You can set the heat in watts coming out of each FET. I'll just leave it at 3 watts and 2 watts. And I'll leave the ambient here. There's airflow adjustment. I'll leave it set to 100 LFM. A future enhancement will be to have no airflow, but for now we really need some airflow just to show how everything works out well. Okay, but now you have 2 FETs and the junction temperature, which is no surprise, is back up high. It's 100, 106, 104. So there's another button here to add a heat sink. So now we just added a heat sink. And look at that. Boom, temperature went way down to 54 degrees and 53 degrees. Let's look at some of the details here. The thermal interface material, this is used as the best one we found, the one we recommended earlier, a few slides earlier. You can take that. You can say, well, what if I'm using a very cheap one instead? There goes the temperature going up. It went from 70 something to 69. That might be good enough, might not. Decide for yourself. I'll go back to the best one. Gap. How much gap right here between the top of the FET and the heat spreader? You can determine that and change that. And there's also a calculator here to actually define a heat sink, aluminum heat sink, the width, the area, and so forth. I'll just leave that as is right now. Now, a question came up before. You can see there's nothing between the FETs in terms of gap filler. What happens with gap filler? Let's look down just using the top FET as an example, 54.3. So I'll add gap filler. And look at that. In this example, it didn't really make much difference. Basically 53.9 to 54.5. So you could say, in this one example, these particular, you might still save the money and not use gap filler. However, if we go down, I'm going to pick a very small EPC GaN FET. This one is 0.9 by 0.9 millimeters. It's still a power FET, but say, let's see, let me take away the heat sink. I think there might still be some bugs here in the system. There we go. Okay, now it's back again. You can see in this case, you have 82 degrees for the top FET. I'm going to add the gap filler. And this did make a big difference. Basically down to 70 degrees. So about 12 degrees Celsius difference by adding a gap filler. So again, this tool is kind of nice because it can tell you just how far you can go. Maybe possibly save money or increase performance depending on which thermal interface material, which thermal pads you use, how much of a gap you can get by with, whether thermal fill is needed or not, and even different power FETs. The different GaN FETs are different sizes, and some of those affect the thermal performance. And in-pad vias. So what if you say, okay, in-pad vias, if your particular design would really rather not have those, I'm going to click this button. It didn't work previously. It's a beta tool, but I'm going to try it anyway. So we're at 82.5 degrees. And oh, it did work. Okay, great. So it goes up to 91 point, basically 92 degrees. So that's saying, okay, without vias and pads and a heat sink, what happens? And you can keep on using this type of thing. And you can also, of course, change the power. You might say the power is not that high there, but I mean, GaN FETs help in the first place by reducing switching loss, and especially for the size, less resistance. So that helps first of all. Then looking at these different options. Let's see, another thing here, you could say, okay, I got rid of the in-pad vias because the board doesn't like those too much. How about changing the airflow? Right now it's set on the lowest airflow, 100 LFM. What if I go to 400? First I'll look and see, okay, 92 degrees Fahrenheit. Click that. And then boom, that goes down to 79 degrees Celsius. I'm sorry, I think I said Fahrenheit before. I meant Celsius for all these. So there we go. And you keep on going with different air speeds, and then take in and put back the gap filler and keep on changing FETs and so forth to get a good optimal thermal system. Over here, some graphs that'll show. This can also help too. Right now, this is a very tiny FET. Again, this is the smallest power FET that EPC makes. So just even the possibility of getting 3 watts into this is really impressive. You can see you're up on this curve here. So increasing to a bigger physical size GaN FET of going way up to 2 square millimeters, which is still very small, will definitely help quite a bit on the thermal design situation. On the other hand, down here, you can see with airflow, if you increase the airflow quite a bit, yes, that'll help, but you can see it's relatively flat here. The curve I was on before is right at the end. That was 100 LFM, now down to 400. Going further won't make a lot of difference. So this is a good kind of look to see what you might want to change. And in this case, going up in size just a little bit to just plain small instead of tiny would help quite a bit there. And I think I'll do that. I'll just go over to this is a FET that's still very small, 2.25 square millimeters. And that sends the temperature down by, I think it was 15 or 20 degrees C. Anyway, this will, like I mentioned, hopefully be on our website later, so you can have all the fun yourself doing designs of the GaN FETs. And again, we're definitely interested in feedback of different features that might be good, or things you see that don't look quite right, or just simply questions on how this looks, how this works. Now let me go back to the main presentation. There we go. That's the end of the live demo. And go page down. There we go. Okay, now a summary. So again, small GaN FETs can be effectively cooled. You can spread the heat flux and use all the layers in the PCB by adding thermal vias, either next to the FETs or underneath the FETs. Also, adding a heatsink is easy, and that has a significant improvement in thermal performance. Using as a baseline in the middle, no heatsink, just a board with vias under the pads. You can see simplifying the board makes the thermal situation not quite as good. Going the other direction, adding a heat spreader, and then adding heat spreader plus a heatsink also provides improvement. And not shown is the further improvements with a gap filler and some other methods such as changing the distance between the FETs and so forth. Okay, for additional resources, on EPC's website, there's an app note, how to get more power out of a high density GaN with a heatsink. And this covers some of the same diagrams in here. There's a video on this also. And you might ask questions like, oh, we can get kind of deep. I'm sure you have lots of questions. Things like thermal cycling. What's up with that as far as reliability and how to optimize that? Questions of underfill. Other kind of questions as far as even not related to thermal, such as voltage and so forth. EPC has a series of very detailed, but yet very readable reliability reports. And the latest one is linked right here. And coming soon is a new book, GaN-powered devices and applications. And I think that's coming this fall, isn't that right, Renee?
Yes, that's the beginning of October.
Okay, yeah, very good. And I think that's the end of the presentation.
Okay, great. Thanks, Brian.
Thank you.
So now we're going to start answering some of the questions that were submitted during the presentation. You can still submit questions by typing them into the Q&A feature at the bottom of the screen, and we'll try to get to as many of them as possible. We had a lot of really good questions. So let's see. The first one was, how do the vias from different nodes, especially switching one, affect EMI?
We found in many cases that we use internal switch node planes to reduce the resistance of the switch node. So I see your point, which is what happens when you have very sharp rising edges and you spread that out further into more planes. It actually works okay because in many designs you can have a bottom plane which can be ground and a switch node internal. But even if it's not an internal, there's a lot of designs with a switch node on the top, and that works pretty well for the EMI. EMI generated with the inductor helps to limit the current going into it. So limiting the current actually helps. There are cases where one option is just slow down the FETs just very slightly by increasing the resistance. But now I'd say if it's a big concern, and putting the switch node in internal vias and connecting those internal vias is probably good. Oh, I'm not hearing you.
I know I was muted. You think after this many months of Zoom, I would know how to do this. Okay, what is the max delta temperature permitted between the heatsink and the other side of the board below the GaN, when temperature is varied from, say, 20 C to 150 to C at the heatsink?
See if I understand that correctly. You're saying the heatsink is very hot, like 100 degrees C, and the board is not so hot. What's the maximum difference between that? Going, I guess, the gradient through the GaN FET?
Mm-hmm.
That question hasn't really come up that much because the conductivity of the GaN FET thermal resistance from the junction to the case is very small. It's like 1 point something in a lot of cases, degrees C per watt. So I don't know. It seems like we don't see that big of a difference. It seems like that would be almost a problem with the tin material if you have that much of a difference between the heatsink surface and the board. So yeah, I think the answer to that would be to investigate the thermal chain and see what's causing that big gap. Is there a problem with the tin material? If I understood the question correctly, maybe I didn't.
Okay. We know vias may generate parasitic capacitance and inductance. How to balance this between heat dissipation and parasitic capacitance?
Yeah, that's in the first example I showed with the optimum layout that EPC does in a lot of the boards and also app notes. With the 3 FETs, the top would be the VN. So that'd be like a DC level VN. So having lots of vias going from that to other layers of VN actually won't affect much. And the capacitor, as shown in one of the diagrams, is right next to the FET. So the source of the current comes from the capacitor on the same layer into the FET. So electrically it'll be good. You won't have added capacitance because of, capacitance and inductance added to that input rail. The same is true at the bottom with the ground. You connect ground to other ground systems, and that should work out well. Now with the switch node in the middle, yes, you could have some, adding inductance typically isn't a problem because with, inductance of that node, because a lot of times it's in series with an inductor. So adding inductance in series with an inductor isn't too bad and might actually help act like a little bead. Capacitance, yeah, that's not good. You don't want to add a lot of capacitance from the switch node to say ground or so. But with layout, with separating the planes by enough, it's a design trade-off. I guess that's the best I could say.
Okay, with in-pad vias under the bump, is there a minimum number of vias required to achieve the best thermal performance?
Hmm, no, the more the better. Each bump would increase the thermal performance. There's reasons not to just perforate the whole thing with vias, which is you start to constrict current flow in other layers. Also, the vias could interfere with each other on the top. And also on the example of a top FET, you would have, if I can go up to that diagram, might be a little bit tough to do. There we go. I think this one. Yep. The one over here, with the VN coming in, coming down here, you don't need any vias here to connect because that's good. So in a lot of cases, you wouldn't have vias there. So you'd have vias on these. And you can see there's a limit to how many you can have just before you get to interfere. You want current to flow down this copper to the rest of them. So it's really a board layout kind of question. But yeah, the more the better in terms of heat flow, but that's not always true for the electrical design.
For EPC GaN FETs, is it better to put the heatsink on top of the FETs or on the bottom on the other PCB side?
On the top, on the top. Yeah, that's that question. That's a very good question. It comes up every so often. And because EPC FETs are not designed to be top cooled or bottom cooled, they're kind of both. There's low, let me see if I can go up a slide or so, because there's good conductivity from both the, from the pads down to the board and from the top out. If you go to a board design, let's see, go back to a diagram. There we go. In this case, a heatsink here on the top has a really great connection because there's no package on the GaN FET, so there's no plastic. This is all silicon. This is silicon wafers. You have great thermal conductivity from the junction in the red bar up to the top, and you put even a thin layer of thermal material to a heatsink. That works very well. On the other hand, if you have a heatsink mounted on the bottom of the board, the heat has to go from here through the pads and down through the board, which is the FR4 material. It's not quite as good as a metal, and then into the heatsink. So if you have a choice, a heatsink on the top is better. Even if you have to put things like inductors and other parts on the other side, if you can put the FETs and their local decoupling capacitors and hopefully a gate driver on the same side, that's the best situation.
Okay. What would be the testing process for thermal model validation to obtain the thermal coefficient for GaN, which could then be used in lifetime calculation?
That's a tough one. What would be the way of calculating the thermal coefficient, which could be then used for a lifetime calculation? That is something I really don't know. I think it's been done experimentally. It's been done with finite element analysis. As far as how that's determined and tested, I don't know. As a field application engineer, I typically start with a data sheet and work forward. But that's a good question to answer later, I think.
So we can we'll check with our thermal engineer internally and get back to you.
Yeah.
I'm just going to make a note that we want to check with Assad. Okay.
Yeah.
Okay. For the same thickness, a GaN die has less thermal resistance compared to silicon. Why is that? The substrate is silicon in both cases.
That's right. Well, maybe it has to do with not so much the MOSFET as a standalone piece of silicon, but the form you buy it or the way you use it. And power MOSFETs, of course, they're lateral MOSFETs, but the high power MOSFETs are vertical devices where you have current come, say, in or out of the bottom, goes through the device, and then comes in or out of the top, and you'd have a lead frame or some way of getting the current from the top back down. So that requires some kind of device, typically a package or something over top. Even a metal package has to have insulation layers, and there's other layers inside a package. So it's not just simply a metal plate mounted on the top of the MOSFET. With a GaN FET, there's basically a silicon wafer with a GaN layer put on it. and that's the way it's sold. That's the way it's with some additional protection, very thin protection layers, but that's basically the way you have it. So yes, you're right. You could start with the same basic die, but to make it usable in a form you'd use in the design, that's the asterisk that I guess the MOSFETs have to deal with. What you end up buying and putting in the design. So just the same with EPC GaN FETs. If we were to do put this in a package and put a big piece of plastic over top and a layer here, the thermal resistance from the junction to the case, which would now be up here, would be greater, and it would lessen the thermal performance. And that's just one reason we're not really too thrilled about packages. Just you would pay for an additional piece of plastic and then reduce the thermal performance out of the top. But the MOSFETs don't have that choice, from what I understand. There isn't a way to really have both all the connections in a lateral way in the bottom with an optimized power MOSFET.
Next question is, why are the vias tented? If they are not tented, isn't the thermal transmission much better?
Well, you kind of have to have the vias tented. You don't want, there's a few reasons. One, you want the, go back to that slide of the vias. Here we go, via construction. So play it over. Yeah, I kind of see what you mean. You want them tented. Well, you want to have as much protection over top as you can. They're plated over, and yeah, you can say that even within the EPC FETs, yes, you have a solder mask, but then you would, you could have an opening for a contact. So I think the most important thing is to make sure that of two things. One, there's a stable fill that stays put, doesn't come in or out, and a nice flat surface, and that flat surface is protected, and no solder comes down. But exactly the different situations of having the solder mask tented, that's probably another good question, unfortunately, to ask of some of our thermal experts.
Okay. Just make a note.
Because I can see a partial tenting might be good enough some of these cases.
Okay. Okay, this question, it might be too, you might need more detail to answer, but maybe not. So we have someone who did some experiments with a GaN FET high side switch at 15 amps without a heatsink. When switched on, the GaN FET did not show any remarkable temperature rise in the beginning, but then suddenly after 10 to 20 seconds, the temperature rises to its extent and the device is burned off. What could be the reason?
What could be the reason? That's a good mystery. If it had if it didn't heat up at first and conducted 15 amps, that's a real good sign, because there's not much thermal mass in the GaN FET. So the fact you have 15 amps flowing through it, and save your finger or other device on the FET and it doesn't seem like it gets that hot, that's good, because it means it can take that. After a few seconds, if it starts to really get too hot and burns up, I'm sorry, how much time? A few minutes, did they say?
So no, 10 to 20 seconds.
Oh, 10 to 20 seconds. Well, it could still be that. I guess depending on what size GaN FET, it could still take a while for the heat to actually get through into whatever's measuring it, wherever that could be. That could be one thing. Let's see, the resistance does go up with temperature, just almost exactly the same kind of curve as MOSFETs. That could be one thing. You could be fine when it starts, then temperature goes up a little bit, and the resistance, I think with both GaN and MOSFETs, about 1.8x, going from say 25 degrees C to maybe 125 degrees C. That can maybe cause the problem. So yeah, that is a little bit maybe too general to answer, but yeah, right into your local FAE field application engineer with EPC, and sounds like a good mystery.
Yeah, I would say definitely have your local FAE look at the whole circuit for you and see what they can tell you.
Right.
Okay. can we use Kapton insulation tape as filler between the heatsink and the GaN surface?
Between the heatsink and the GaN surface. So in other words, a heatsink up here, and you put Kapton tape on. Yeah, I think the answer is yes. I'm not sure about the thermal conductivity of Kapton tape, but well, just a point of trivia on the bottom, polyimide. If you look at the bottom of GaN FETs, they look kind of orange. That's polyimide, which is basically it's the non-brand name for Kapton. So you could basically say the Kapton tape already comes on each GaN FET on the bottom, even though it's not the tape form of it. So putting it on top should be okay. But again, just I don't know the thermal conductivity of Kapton tape.
Okay. Are there any other metal materials for heat sinks suggested other than aluminum?
Yes, there have been a lot of people using steel, because if you have a steel enclosure and that's what you're given, then like a big steel chassis, then that's fine too. It doesn't conduct as good, but if it's if it's big and the metal chassis is bolted to something else, that can be just fine in many cases. It's almost like what you're given is one thing. So yeah, copper plates is one example, and aluminum are the main two. We got steel, and there's probably somebody out there who's looked into or has used thermally conductive plastics. I don't know if anybody's done that, but that might be something interesting to look at. I don't know if plastics would be good enough to be an effective heat sink. Maybe not, but there are such things out there.
Which helps better for heat spreading, bigger via holes or higher number of vias?
I don't know the answer to that, but that's something that we hope to
We'll check with Assad.
Yeah, well, not only check with Assad, but
yeah, maybe you can.
in the future, as we make this available on this thermal model, you click on vias, and right at this moment it makes an assumption, but you could put the density of them,
right,
how many there are, or the number of millimeter squares. So this is, you can pick how many you have. So yeah, you might get to a point where adding more thermal vias just doesn't really do much. I think you have to look at see if there's a curve there. So yeah, I think that's a good determiner of your individual situation.
So a question about the simulation tool: will it have temperature over time for pulsed applications?
As of this moment, no, that's not in the plans for it. I know what you mean. I think you mean things like one very popular use of GaN FETs is for things like pulsing lasers for like LiDAR and so forth, and other kinds of pulsing things. And there, you'd want to calculate the heat there for those things. No, as of this moment, this is basically considers a DC power loss coming out of the FETs. But I mean, yeah, it's a good suggestion for future enhancement, because we have the curves for a pulse and what that does as far as conducting through the GaN FET.
Okay. Let's see. Have you estimated the impact or improvement with forced ventilation?
Let's see. I think I showed that a little bit with the graph right down here. So if you pick a FET you want, you can see from 100 LFM down to 1,000 LFM, you can kind of see a curve how much improvement there is. Maybe the question is without, could you restate the question again?
Have you estimated the impact / improvement of forced ventilation?
Yeah, this model doesn't, compared to no ventilation, yeah, this model doesn't cover that yet. There would have to be some conduction to something else. So no, that hasn't been done.
Okay. How much of a difference would vias in pad with a conductive fill in them make to the thermals? The vias shown so far seem to be non-filled ones.
That's right. The diagram, yeah, this is kind of deceptive. Yeah, it looks like non-filled, but we actually recommend non-conductive fill. So the question is how much improvement if you take this via instead of non-conductive fill, put in conductive fill. The thermal conductivity is dominated in that case by the walls, by the copper and the walls of the via. And it was found that by going to conductive fill, the conductive fill isn't as good as copper. I mean, it's okay, but it's not great. So there's only minimal improvement. Yeah, I mean, if you're up for each little bit, but then you have to have the trade-off of the board house. Like, is it what you want? Is it stable over temperature? You have to make sure there's no outgassing. Everything else does what you want it to do with a conductive via, a conductive fill in the vias. So we reached the conclusion that because the board houses, because of minimal impact, non-conductive vias probably the best.
Okay, so just quickly, I just want to be sensitive to everybody's time. We are at the hour. Brian, you have time to stick around, right? Because we still have questions. If you want to stick around, and that's fine. We'll try to answer as many questions as we have here. And then if you need to go, that's fine as well. A copy of the presentation and the recording will be up on the website within the next day or two. So you can come back and listen to any questions you missed. If we didn't answer your question and we answer it when you're gone, then you can listen to it on the recording. Or if you think of another question after you go, feel free to send it into info@epc.com or epc-co.com, and we will we'll get you an answer for that. So anybody that needs to go at the hour mark, thank you for joining. And again, send us in any questions you have that come up afterwards. And anyone who can stick around, we'll keep answering questions here. So let's see, okay, so we have one says, a practical design question. I have a total loss of 2 watts on a FET and its thermal resistance is 31 degrees C per watt. Do you think the FET can survive without airflow and heat sink? The calculation gives 90 C, but the test shows much higher.
The test shows much higher. Yeah, there's a few things that can account for that, such as the heat. When the temperature goes up, the resistance goes up, and that can cause like a general increase in temperature. That could be one thing. Yeah, that maybe is a little bit too specific, but please write in with details. So maybe we can look on that and talk about that some more. And also that once we get this out on the web, we'd love to have feedback such as this type of thing too, because we want to have this be an accurate model. This would not be viewed as something to be overly optimistic. That wouldn't serve either one of us very well. On the other hand, don't want to be overly pessimistic with the results and have a bigger heat sink that's really needed. It sounds like the question kind of results from a design that maybe had overly maybe optimistic board. But even there, a lot of the thermal information given in the data sheets, including EPC, everybody's in the same boat, uses like the 1 square inch of copper in a board to get the thermal resistance or thermal to air and so forth. So if things are different from that one particular situation, then it's not applicable to everything. And it assumes no other heat sources too. The information it uses to make everybody's heat sinks, data sheet for thermal calculations.
Don't know if you know, but do you know which thermal camera we recommend for measuring our GaN FETs?
We've used a lot of the Fluor cameras. I think that's the biggest name. I think that's one we use. That's there's different accuracy of those. you don't necessarily need real high resolution. It's good if you have a field of view where you can put it down closer to the board. The GaN FETs are small. One thing that's also helps is to have the GaN FETs painted with a particular black paint, so that the image shows a good thermal measurement. In other words, a shiny surface won't give a good thermal reading with a thermal camera. But if you have you could write to any one of us EPC engineers. There's a application engineer who has a specific paint part number that he's used, one or two of those that we can help with that. So you have a good image of the board, and it gives the best thermal reading off the FET with a non-reflective black paint. But yeah, so, some fluoro ones. There are some low-cost ones. I think you have to make a judgment of how much accuracy you really want.
Okay. How different will the soldering heat profile be of the switch that has the via in pad?
It should not be different at all. That's the goal of working with it. And going back to the get the slide sorter and going back to the via one. Here we go. Yes, the goal is to have, when this is played over, to have this very flat, so you can't tell by looking at the board whether there's a via underneath that pad or not.
Okay. Let's see. Temperature. Let's see what this says. Okay, the heat sink temperature is varied from 50 C to 150 C at the heat sink. What would be the thermal spread at the bottom side of the board opposite of the GaN?
So the heatsink varies from 50 C to 150 C. Is that?
Mm-hmm.
And what's the
heatsink temperature is varied through the heater from 50 C to 150 C at the heatsink.
Okay.
What would be the thermal spread at the bottom side of board opposite to the GaN?
I think it depends on what's on the bottom side of the board, if it's connected or whatever. If there's no, it's probably very similar to the GaN. It might be very close to the GaN. If there's no heat flux through it. I'm not sure if the questioner is trying to ask, okay, if you have a heatsink assembly, you put a thermal probe on the bottom, is that close enough? Does it get close enough to the junction of the GaN FET to do an accurate measurement? It could be, but it's kind of a little bit dangerous to do that and assume that's a good way of measuring. It really depends on the board and that particular board and how much gets radiated from the board. One thing that can be done possibly if you need to make measurements is to put a little probe on the side of the GaN FETs, and you can calculate from the junction to the top kind of the gradient there and put the thermal couple right against it and get some good idea of where that is. But yeah, the area of thermal measurements is not always clear, not always easy to do.
A higher number of vias helps in reducing the temperature at the upper layer, but what about when there is a multi-layer board? The lower layer gets affected. How do we take care of that?
Yeah, that's true. The other layers do get affected, and that's kind of the point. The idea is to get the heat coming down to these bottom layers. So yeah, you're right. I mean, if you have other parts on the bottom side, yes, they will get heated because they'll spread the heat from just the top and the more vias. Whoops, I'm sure we did there. I hit the P button. Oh, here we go. Okay, yeah, so that'll it will heat up the other layers, but that's actually good. That means the heat is spreading like you'd want. I guess there are some cases where you might consider that bad, like you wouldn't want the other side of the board to heat up. And in that case, you might have to not have vias if that's really important. and use some top side cooling instead.
Can high transient current spikes cause thermal shock to the FETs or create local hotspots within the die, say a couple of 100 amps for microseconds?
Yeah, there's thermal transients. Yeah, and that's detailed in our data sheet. There's curves in the data sheets near the back, typically like the second or third page from the back, that shows the thermal transient response of the GaN FETs with pulses. So yes, you should look at those and see, because yeah, like a big high current shock is supported. A lot of designs use that for, say, LiDAR and other kinds of pulsed ones. But the thermal design, yes, it is more complicated. This whole presentation today is kind of based around the concept of basically DC power coming out of the FETs. But yes, contact us definitely for those kind of questions, or the back of the data sheets for the initial curves to help that. And there are thermal models with capacitors. Like all these models here we're showing show resistors to model the current. There's other models we have for each FET, and they're on our website, and we'd be glad to help you find those, that show resistors and capacitors. So like an AC kind of current, a thermal model that we build up, and you can then use in your simulation program to do that kind of work.
In the last few years, some semiconductor vendors proposed a source down package. The idea was because large amount of current flows under the gate, hence most of the heat was generated near the source terminal than near the drain terminal. Is this also the reason why the heatsink on the top of the EPC device is more effective?
No, I think that's more for MOSFETs. And again, I heard that too. I don't know the details of it. Yeah, I heard that type of thing too. Source down. On the GaN FET, everything is down. The layer, basically the top 90+% of the GaN FET is inert silicon wafer. It just kind of sits there. It's like a holder for the GaN layer. The GaN layer is a thin layer that exists right here. So the current comes into the bottom and leaves from the bottom, and the heat is generated more or less evenly. And there's thermal diagrams for each FET we have on the thermal model for each FET, but it's kind of evenly throughout the FET here on the surface. So yeah, that doesn't really apply. So the top isn't the drain heat or the source heat. All the heat is in the bottom, and the heat there just conducts from the bottom to the top. It doesn't form it near the top.
Okay. So on the simulation tool, we got a feature request already, Brian. So you're asking
Okay, good.
So it says, can we get a history of detailed reports viewable side by side to make change comparisons clearer? So when you have different scenarios, want to look at the results side by side, perhaps add delta values for those parameters that changed from the previous detailed report and highlight those input parameters that changed with a different color.
Yeah,
that's really good feedback.
Yeah, I didn't show that, but there it goes. This probably isn't the kind of detail you want. I think I kind of know what you mean. I think you probably mean almost like a screenshot type of thing or something. But we do have this minimal so far. So yeah, that's actually a great suggestion. Right here, there's a save report, but it's very minimal. It basically just takes this. So I think you're talking about maybe expanding that to all the conditions. So as you change things, you don't get confused about what you saw, what you didn't see.
Right.
Yeah, that's great.
Okay.
Thanks.
Then can you show the name of companies for filler and thermal pad, which you showed in your presentation slides? Do we have like a list of the recommended suppliers? And I don't know if they're in here.
Let's see. We have
some of them had part numbers, but
yeah, we do have some of those. Let's see, where is that? Maybe it's in the phase 12 report. I can't remember, but
okay.
We have part numbers here for the mechanical assembly, and we also have let's see, for the thermal gap filler. This is the light blue. we have this Bergquist material.
Okay.
Now for the TIM, the grayish kind of material, the top thermal pads and so forth, the good one there, let's see. This have it? Yeah, this is an example of one of the best performing ones we've seen.
Okay.
So I get, yeah, here's the part number and here's the key performance spec for it. But there's a wide range. And again, I wouldn't be, it's not like EPC recommends one or recommends another, because there might be conditions where you would say, well, we need the best, and this is the best performing, or you might say we need the best cost performance ratio, or you might say for consumer electronics, you might need something that barely works well enough. And there's some of those out there too. So yeah, we'd be glad to share some, as long as you don't take that as being that's the one and only thing to use.
Okay. Well, thank you, Brian, and thank you everyone for sticking around and all the really great questions that we had today. Again, if you have any other questions come up following the webinar or after you watch the recording, just feel free to send those into info@epc-co.com, or you can always submit a request via the Ask a GaN Expert feature on the website. You should receive